A chatbot hallucinating a weird recipe for like a chicken salmon fusion pie? That's just a funny internet joke.
Right. You take a screenshot, you post it, and you just move on.
Exactly. We all laugh. But an autonomous AI hallucinating while it's executing $1 million financial trade.
Oh, yeah. That's a totally different story.
Or autonomously deleting client records because it,
Yeah.
just misunderstood a prompt. That is an enterprise disaster.
A complete disaster.
So welcome to another deep dive. Today, our mission is to shortcut your path to understanding the architecture that is actually going to prevent those disasters.
Because the stakes are incredibly high now.
They really are. We are talking about agentic AI today, and we've got a fascinating stack of source material to go through.
We really do.
Specifically, we are looking at Antonio Gali's comprehensive book, Agentic Design Patterns. Plus, we have some incredibly sharp insights from industry leaders like Goldman Sachs CIO Marco Argenti.
And it is a profound transition that we are witnessing right now. I mean, for the last 18 months or so, the public has just been totally mesmerized by models that simply process information and generate text.
Right, the basic chatbots.
Exactly.
Yeah.
But we are moving rapidly from machines that just talk to intelligent systems that can actually reason, plan, and physically act to achieve complex goals.
Okay, let's unpack this because we are no longer just, typing a prompt into a single model and crossing our fingers.
Not at all.
We are talking about building entire digital workforces, like literal teams of AI agents.
Yes, teams of agents working together.
But before we get into the actual engineering blueprints, we need to establish what an agent actually is in this context and why the tech world is suddenly so obsessed with them.
Well, at its core, an agentic system is basically a computational entity. It is designed to perceive its environment and take independent actions to achieve a specific goal.
So it's not just waiting around for you to press enter.
Right. You can think of it as a major evolution from a standard large language model. An agent actually operates on a continuous 5-step loop.
Okay, what's the first step?
First, it receives a mission. And this could be something highly ambiguous, like organize my team's weekly schedule.
Wow, so not even a specific command, just a general goal.
Exactly. Second, it scans the scene. It doesn't just sit there. It actively gathers context by reading your emails, checking calendar APIs, and, just assessing its digital environment.
That is wild. And the third step?
Third, it thinks it through. It calculates the optimal sequence of actions it needs to take. Fourth, it actually takes action.
Like sending the actual calendar invites.
Right, sending the invites, booking the Zoom rooms, whatever it needs to do. And crucially, there's a fifth step. It observes the outcomes of those actions.
So it checks its own work.
Yes. It learns if it made a mistake, and then it updates its approach for next time.
That is a massive leap from just asking a system to write a poem. I mean, it is genuinely autonomous.
It really is.
And in the source material, Marco Argenti provides this brilliant analogy for why this shift is happening right now.
The car and the engine analogy.
Yes. He argues that if the recent explosion of large language models was basically about building the engine, the era we are entering today is about building the car around it.
Which makes perfect sense. I mean, an engine sitting on a test block is incredibly powerful, sure, but it doesn't actually take you anywhere without a chassis, a steering wheel, and a transmission.
Right, you need the whole vehicle.
Exactly. The language model is just the raw cognitive power. The agentic frameworks, the design patterns we're going to explore today, those are the car.
And Argenti notes that the stakes for building this car correctly are just astronomically high. He actually calls it the builder's mandate.
Yes, the builder's mandate. Because you cannot simply overlay these powerful new AI tools onto messy, inconsistent legacy systems.
It just won't work.
Messy corporate systems plus autonomous agents equal a recipe for disaster. I mean, in the old days of computing, we used to say garbage in, garbage out. But in the era of language models, an AI trained on garbage data doesn't just produce obvious garbage.
It produces confident garbage.
Exactly. Highly plausible, completely incorrect outputs that can just silently poison entire enterprise processes before anyone even notices.
Okay, I hear what Argenti is saying about this builder's mandate, but I have to push back on this underlying premise just a bit.
Sure, go ahead.
If these models are already so incredibly smart, I mean, they are passing the bar exam, writing functional code, why do they fail so spectacularly when we ask them to do complex multi-step tasks?
That is the big question.
Like, why do we even need to build this complicated car? Won't the next generation of models, just through raw computing scale, be smart enough to not need all these workarounds?
Well, it is a very common misconception that sheer scale solves everything. If we connect this to the bigger picture of how these models actually process data, the limitation is purely structural.
Struck.
A single massive prompt just overloads the model's working memory or its context window. When you give an AI a 50-step problem in one breath, it suffers from what researchers call instruction neglect.
Instruction neglect. Yeah.
Okay. It fixates on the beginning and the end of your prompt and entirely loses track of the middle steps.
Oh, wow. So it just forgets what it was doing halfway through.
Exactly. And small errors in reasoning at step 2 will compound exponentially by step 10, which leads to hallucinations. We need structural blueprints to manage the AI's cognitive load and force it to maintain discipline.
It feels like handing a brilliant but incredibly scatterbrained professor a massive to do list and just walking out of the room.
That is a great way to put it.
They might write a genius level thesis on step 3, but then completely forget to do steps 4 through 50 because they got, distracted by their own thoughts.
That is the exact dynamic we are dealing with. And that is exactly why we require design patterns. We have to mechanically structure their workflow.
Okay, so if giving the scatterbrained professor one big list breaks their brain, how do we force them to put on blinders and just do one thing at a time?
Well, this brings us to the first major design pattern from Gully's book. It's called prompt chaining, which he refers to as the sequential engine.
The sequential engine.
Right. Instead of giving the AI one massive monolithic problem, you decompose the problem into a rigid sequence of smaller, highly constrained subtasks.
Okay.
The crucial mechanical rule here is that the output of one step becomes the direct mandatory input for the very next step.
The sources gave a really helpful historical example to visualize this. Imagine you ask an AI a complex query like what caused the 1929 stock market crash and how did government policy respond?
Which is a huge question.
Right. If you just lob that into a standard chat window, the system might just blend a bunch of vague facts together. But under the hood of a prompt chaining system, it functions like a factory assembly line.
Exactly like an assembly line. The first agent in the chain is instructed solely to extract the sub-questions from your query.
That is its only job.
Yes. It identifies two distinct parts: causes of the crash and government response. Then it hands that structured breakdown to the second agent.
Okay.
Agent 2 researches only the causes of the crash. It passes its notes to Agent 3, who researches only the policy response.
So they are completely siloed.
Very siloed. Finally, Agent 4, the synthesizer, takes the findings from steps 2 and 3 and writes a coherent, highly accurate answer. By forcing the AI to focus on one micro task at a time, you eliminate that instruction neglect.
But the sources highlight a strict engineering rule for this to actually work. This assembly line completely falls apart if the data isn't passed perfectly between the steps.
Oh, absolutely. The handoff has to be flawless.
The book mentions forcing the AI to output machine-readable formats, like JSON.
Yes, JSON is very standard for this.
So for those of us listening who don't dream in code, is JSON basically just a way of forcing the AI to fill out a highly specific digital form, rather than writing, a conversational paragraph?
That is a perfect translation. If Agent 2 hands a messy conversational paragraph full of pleasantries to Agent 3, Agent 3 just gets confused.
Like saying, here's my research, hope you're having a good day.
Right. The AI tries to process the pleasantries and loses the plot. So JSON, or JavaScript Object Notation, strips all that conversation away and organizes the data into strict key value pairs.
Just the raw data.
Just the data. It acts as a standardized digital handshake between the ages, ensuring the data moves down the assembly line without any loss of fidelity.
Okay, so prompt chaining sounds incredibly effective for predictable tasks. If we are manufacturing the same metaphorical car over and over, the assembly line is great.
Exactly.
But what if the input is total chaos? I mean, an assembly line completely shatters if you suddenly throw a washing machine part onto a conveyor belt designed for steering wheels.
That would definitely break the machine.
Right. So if a user's request is totally unpredictable, how does the system know which chain to use?
The system requires a traffic cop, and this is the second pattern: routing, or the logical arbitrator.
Routing. Okay.
Routing introduces conditional logic into the agent's framework. Instead of a fixed sequential path, the initial AI layer evaluates the user's intent and dynamically directs the flow of information to a specialized tool or a specific sub-agent.
The classic example in the text would be a customer support bot for a massive retail company. A user types a frantic message into the chat. The router agent analyzes that text.
Right, it reads the room. essentially.
Yeah, and if it determines the intent is to check order status, it routes the workflow strictly to a database lookup tool.
Which is very straightforward.
But if it reads the text and determines the intent is technical support, it routes the user over to a specialized troubleshooting agent.
Exactly. But the mechanics of how that router agent actually makes its decision are what make this pattern so robust. You could just use an LLM to analyze the text and output a category keyword.
Sure.
But more efficiently, developers often use something called semantic vector similarity.
Whoa, hold on. Semantic vector similarity.
I know, it sounds intense.
In plain English, does that just mean the system is matching the mathematical vibe of the user's words against a database of known categories rather than looking for exact keyword matches?
Yes, essentially. It turns the meaning of the user's sentence into a coordinate on a multidimensional map.
Oh, that's wild.
Right. So if the user's sentence lands geographically close to the coordinate for shipping problems, the system routes the request there, even if the user never actually typed the word shipping.
It is triage at light speed, getting the right unpredictable problem to the right specialist.
Exactly.
All right, so our system can now break tasks down sequentially on an assembly line, and it can route unpredictable tasks to the proper specialist using mathematical vibes.
Which is a solid foundation.
It is. But here is the next operational bottleneck. What happens when a routed task requires gathering a massive amount of information from multiple different databases?
That is where things slow down.
Yeah, if the agent does this sequentially, querying database A, waiting for the digital handshake, then querying database B, waiting again, you, sitting at your keyboard, are going to be waiting forever.
You really are. Sequential execution is a massive bottleneck when an agent relies on external operations, like searching the internet or pulling data from third-party software.
So how do we fix the wait time?
To solve the latency issue, we implement the third pattern, parallelization, or the accelerator. This basically forces the system to run independent subtasks concurrently, rather than waiting in line.
The research team example from Gully's book illustrates this perfectly.
Yes, that's a great example.
Let's say your mission is to research sustainable technology trends. Instead of one single agent reading articles one after another for an hour, the system instantly spawns 3 distinct agents.
All working at the same time.
Right. Researcher 1 is deployed to pull data on renewable energy. Researcher 2 hits the internet to analyze electric vehicles. Researcher 3 dives into carbon capture. They are all executing their searches at the exact same millisecond.
And because those 3 topics don't depend on each other, they don't need to wait for one another.
Makes sense.
Once all 3 parallel tracks complete their research, a final specialized program called a merger agent takes their independent data sets and synthesizes them into a single cohesive report. You've just cut your processing time by 2/3.
Here's where it gets really interesting, though.
Okay, what's that?
If we have all these autonomous agents running around concurrently, pulling data from all corners of the internet at high speed, haven't we just invented a high-speed misinformation machine?
Oh, absolutely. That is a huge risk.
Like, if researcher 2 pulls hallucinated data about electric vehicles, the merger agent is just going to confidently stitch that lie into the final report. Fast garbage is still garbage. How do we stop them from going off the rails?
Well, you've identified the core vulnerability of autonomous agents there. Speed and autonomy are really dangerous without oversight.
So what's the safety net?
To solve this, developers use the 4th pattern, reflection, which operates as a self-correcting loop. Think of it as an internal quality assurance department.
Okay, QA for AI.
Yes. Before the system ever shows you a final result, an agent evaluates its own work, or the work of a peer, and uses that evaluation to refine the response.
The sources detail a specific mechanism for this called the generator-critic model. But if an AI is just checking its own work, doesn't it inherently agree with itself? How do you prevent that cognitive bias?
What's fascinating here is that you prevent bias through strict role separation and distinct system prompts. You literally sandbox them from each other.
Okay, how does that work?
Agent 1 is the producer. Its entire operational focus is on generating the draft or writing the code. It is designed to be creative and expansive.
Just generating content.
Right. You then pass that output to Agent 2, the critic. The critic operates under an entirely different set of rules. Its only job is to be adversarial, to find logical flaws, check facts against the original constraints, and enforce quality control.
Wow. It perfectly mimics human peer review. The producer writes the essay, the critic takes a red pen to it and says, you missed a citation in paragraph 3, and this mathematical formula is wrong.
Exactly.
And then it just kicks it back to the producer to fix.
That's it. The trade-off here is computational cost and time. Reflection loops dramatically increase the number of tokens the system processes, which obviously costs money,
All right.
and it adds latency because of the iterative back and forth. However, if you are relying on an agent to write software code or conduct financial analysis, that trade off is absolutely mandatory for safety.
Okay, so we now have these four distinct, incredibly powerful tools in the toolbox: chaining, routing, parallelization, and reflection.
The core building blocks.
Right. But how do these independent patterns know what they're looking at? If the routing agent talks to the parallel agents, how do they share a brain across all these different steps without losing the plot?
Well, in a production environment, you don't use just one of these patterns. Real world applications orchestrate all of them simultaneously into what the text calls the composite agent.
The composite agent.
Yes, a user request enters the system and gets routed by the traffic cop. That route might trigger parallel tracks to gather data from three different APIs concurrently.
Okay.
That data is then chained sequentially into a synthesis step, and that drafted synthesis enters a reflection loop for quality assurance.
But the invisible glue making all of that possible is a discipline called context engineering?
Yes, context engineering is the foundation that keeps the scatterbrain professor grounded. It is the systematic discipline of building a highly curated operational picture for the AI before it generates a single word of output.
And it relies heavily on techniques like RAG or retrieval augmented generation, right?
Exactly.
To clarify RGAF for a moment, that's essentially giving the AI an index of verified company documents it has to look up and read before it tries to guess an answer, correct?
Precisely. It retrieves the facts first, then augments its generation with those facts. But context engineering goes beyond just handing it documents.
What else does it include?
It integrates short term memory of the current conversation, long term memory of the user's preferences, and the current state of the system itself.
The book points out something crucial here. Just giving an AI a massive textbook of context is actually counterproductive.
Yes, very counterproductive.
It causes that cognitive overload we talked about earlier. It's exactly like prepping a surgeon before they walk into the operating room. You don't hand the surgeon a massive binder containing the patient's entire medical history from birth.
They don't have time to read that.
Right. You give them the precise vitals for right now, the specific x rays of the organ, and the exact surgical tools they need for this specific cut.
That's a great analogy. Advanced models will drastically underperform if given a cluttered view of their environment. Context engineering curates the model's limited attention.
So it only sees what it needs to see.
Yes, it ensures the AI has exactly the right information and strictly only the right information at exactly the right moment in the workflow.
Having mapped out the anatomy of how these agents work today, if you're sitting at work right now thinking, great, when does this thing actually take my job? We need to look at where this is heading.
The final section of Gully's source material shifts from current engineering to future states. He outlines 5 distinct hypotheses for the evolution of agentic AI.
And we are moving rapidly towards systems that are deeply integrated into our physical and economic reality.
We really are.
Let's explore these because they escalate quickly. Hypothesis 1 is the rise of generalist agents.
Right.
Right now, agents are narrow. They do one thing well. The shift here is moving from a digital assistant to a fully autonomous project manager. Instead of asking an AI to draft an email, you tell it, plan a 30-person company offsite in Lisbon for next quarter.
The mechanism behind this is what makes it revolutionary. A generalist agent would maintain state over several weeks.
Weeks.
Yes. It would autonomously interface with airline APIs to monitor and purchase flights, parse vendor contracts sent to its own inbox, negotiate rates based on a strict budget constraint you provided, and handle dietary restrictions by emailing your team directly.
It just handles the entirety of the operational friction.
Completely.
Then
Yeah.
hypothesis 2 is deep personalization. This is the shift from a reactive tool that waits for a prompt to a proactive partner.
Right. It anticipates.
Yeah, it monitors your background data streams, your communications, your calendar, your project deadlines, and it anticipates bottleneck before you even see it, offering a drafted solution without you ever asking.
Which naturally leads to hypothesis 3, embodiment. The realization that the physical world is messy and a digital brain trapped in a server is fundamentally limited.
Right.
Embodiment bridges the digital physical divide by integrating agentic AI with physical robotics.
Right, because my digital calendar agent is great, but when the pipe bursts under my sink, it can't, plunge my toilet or fix the leak.
Exactly. An embodied agent utilizes vision sensors to look at the leaky pipe, Uses its LLM reasoning to identify the specific valve failure, formulates a repair plan, and then translates that plan into kinetic action.
So it uses robotic actuators to physically turn the wrench and fix the plumbing.
That is the goal, yes.
Hypothesis 4 introduces the agent economy. This is where things get wild. We are looking at highly autonomous agents acting as independent economic entities.
This one is fascinating.
Imagine a single human entrepreneur launching an agentic system to run an entire B2B e commerce business. The agent monitors social media for emerging trends, autonomously spins up marketing campaigns, interfaces directly with manufacturing APIs and oversees supply chains to order inventory, and dynamically adjusts pricing on the website every hour to maximize profit margins.
In that scenario, business to business commerce increasingly becomes AI to AI commerce. Your supply chain agent negotiates wholesale rates directly with a manufacturer's sales agent.
Without human intervention.
Right. It operates at a velocity and scale that human operators simply cannot match.
So, what does this all mean when the system hits a wall? If that e commerce agent suddenly realizes the company's website is loading too slowly and it's killing sales, what does it do? That brings us to the fifth and arguably most mind bending hypothesis from the text.
The fifth hypothesis is the emergence of metamorphic systems.
Metamorphic systems.
Yes, these are goal driven, multi agent architectures that possess the ability to dynamically rewrite their own foundational code and modify their own topology to achieve a declared goal.
Let's really break down the mechanics of this because it sounds like science fiction.
It does.
If the agent hits that website bottleneck, it doesn't just send you, the human, a diagnostic error report saying a website is slow. It fixes it.
Yeah.
But how does it do that without breaking its own core programming?
It utilizes an advanced dynamic version of the design patterns we discussed earlier. When it identifies the bottleneck in the web architecture, the system autonomously duplicates itself.
Wait, it clones itself?
Essentially, yes. It spins up 3 new, temporary parallel agents. It assigns them to a secure sandbox environment. Those agents generate new code for the website, use reflection loops to test that code for bugs, deploy it to a small percentage of live traffic, evaluate if the new code actually increased conversion rates, and if successful, they permanently implement the new architecture.
And then what happens to the clones?
Once the goal is achieved, those temporary agents just dissolve back into the main system.
It is literally re-architecting its own digital structure on the fly. You declare the what, and the system completely engineers the how.
It is the ultimate expression of the agentic paradigm. The system observes an inefficiency in its environment and structurally evolves to overcome it.
To wrap this all up, the through line of everything we've covered today is that we are no longer just interacting with static databases, we are managing digital workforces.
That is the key takeaway.
By understanding these core blueprints, chaining to force focus, routing to direct traffic, parallelization for speed, reflection for quality control, and context engineering for a shared brain, you are now equipped to understand the systems that will undoubtedly define the future of work.
But understanding the architecture is only half the mandate. This raises an important question, circling back to Marco Argenti's insights.
Right.
Building these systems demands immense architectural responsibility. The goal of deploying agentic frameworks is not to replace human ingenuity, but to augment our capabilities. It requires developers to rigorously define operational purposes, anticipate failure modes within those reflection loops, and build systems that are transparent enough to inspire enterprise trust.
And I want to leave you with one final lingering thought to mull over. If we really are accelerating toward that fourth hypothesis, the agent economy, where your personal autonomous AI agent is negotiating, buying, and selling with corporate autonomous AI agents at microsecond speeds totally impossible for humans to track. What happens to the very concept of economic value?
It's a huge shift.
It really is. When algorithms are the ones making the purchasing decisions based on mathematical utility rather than human emotion, who is actually the consumer? We started this deep dive talking about the shift from machines that just talk to systems that actually do. It seems our scatterbrained professor has not only learned to focus, but they might just be running the global economy sooner than we think. Thanks for joining us on this deep dive into the architecture of tomorrow.